I'm going to present you a talk about the analysis of susceptibility data of a room temperature superconductor at high pressure. Work is done in collaboration with Jorge Hirsch, and the results of that I will talk about are described in those in an archive paper and in two journal papers which emerged out of this archive paper. And also you will be able to find the slides of this presentation with those citations on my personal website on the address indicated below. The outline of the talk is I'll start with a short introduction about superconductivity, then tell you about the published susceptibility of this room temperature superconductor, and then about the raw data, and then present a diagnosis of the published susceptibility data and the diagnosis of the raw data, and then with a summary. Superconductivity was found in 1911 by Kamerlingh Onnes in mercury as a drop of the resistance to zero resistance at about 4.2 Kelvin. One consequence of this zero resistance state is also that there should be perfect diamagnetism in the susceptibility, and so chi should be minus 1 over 4 pi. And so these two are more or less equivalent phenomena, and there's an additional phenomena which is known as the Meissner effect. This involves not varying the magnetic field, but just keeping it fixed and then cooling down temperature of your superconductor, going from the normal phase into the superconducting phase. And what you find there in a superconductor is that the flux gets expelled. This was found in the 30s, so long after the original discovery of superconductivity. And together, these two things, zero resistance or perfect diamagnetism and or perfect diamagnetism, and the Meissner effect, those two phenomena together define what we normally call a superconductor. And so that's the burden of the experimentalist to actually demonstrate these two different kind of features in order to demonstrate that you have a superconductor. Superconductivity is a phenomenon that exists now more than 100 years, and over time materials have been found with ever increasing TCs. So it started around 4 Kelvin, but then in other elements it went up, being the highest in niobium, and then going on to alloys and then into metallics to about 23 Kelvin. And then with the advent of cuprate superconductivity by Becknotz and Müller, say TC went up enormously above the liquid nitrogen limit by the work of Paul Chu and way beyond. And then actually it was a very interesting intermediate period also of finding high TC superconductivity in iron-containing compounds. And then because the great work of Michael Ermetz, the new era of hydride superconductivity started with H3S, soon to be followed by lanthanum hydride. So that was sort of the situation in 2020. Then, on 14 October 2020, a paper appeared in Nature. When I saw it, I was super excited and sent it right away to all members of my group, and now got it. So this is carbon sulfur hydride, which under pressure, again, very high pressure, shows resistive transitions up to 267 Kelvin, even a bit higher. There's one extra trace not in this graph. And very sharp transitions also. And also the susceptibility shows very nice drops. Susceptibility here is in units of nanovolts, so this is not calibrated for sample size or anything like this. More or less raw data. There's one modification as indicated in the paper. The background signal, there has been a subtraction of a background signal to obtain these data, which was necessary because there's a very big background signal coming from the pressure cell, of which, of course, you also get the susceptibility signal. And so that has been determined by simply changing the pressure to 108 gigapascal, so that there is no superconducting transition. It's just non-superconducting, more or less constant everywhere. And that has been subtracted from the data. Very clean experimental method. So that's why what you see in the susceptibility is around 0 above TC, and then drops to something like -15 or so nanovolts below TC. for all 6 pressures shown in these two different graphs. Then there was a lot of pressure from Jorge Hirsch in particular to get access to the raw data and also the data sets as they were in the graphs of this figure, of this paper. And so they came out in December 2021, which is a bit more than a year after the original publication in Nature. So it was published for all of the 6 different pressures, the measured voltage, so the susceptibility, including also the pressure cell, and then the same thing, but then from which this background had been subtracted. So that is the measured voltage minus a background. The background itself was not published, but it should have a very simple relation to the other two, simply given by the arithmetics given above. So if you have measured voltage and superconducting signal, you subtract superconducting signal from measured voltage, and that should give you the background signal. So in principle, you have all 3 over here. In this graph, we just summarized again those 6 pressures. This is now our own graph, just using those data from this tables. And the blue curves correspond to what I showed before. That's the superconducting signal. And the green curves, that's the measured voltage. Let's take the example of 138 gigapascal on the top left, where you see that the superconducting signal has a scale going from -20 to +60. The measured voltage goes from 14,140 to 14,240. So it's the same dynamical range, just shifted by 14,000 about. And this 14,000, that is what this background signal is. That's all coming from your pressure cell, essentially. And then you have similar kind of ratios for the others. So there are about 3 orders of magnitude higher background than there is sample signal. And so that's quite a challenge for an experimentalist, of course, to separate these 2 different things. Now, there was a thing that Jorge immediately pointed out in December already, and that's actually where he contacted me, being an experimentalist, and asked, is there any way that you can see that if you subtract 2 independently measured signals, measured voltage and background, each containing noise, that you would get a superconducting signal which has less noise than the measured voltage, as you can see very clearly in this example. There's more noise here than there is there. And if you look carefully at all the other examples, it's the same for all 6 pressures. So the data indicate that the noise level is smaller in the superconducting signal than in the measured voltage, but it should be bigger because you add or subtract 2 signals having independent noise. Each being added up should be more noise and not less noise. So I thought a bit about it and said immediately, actually, or very soon, okay, it could be just that they smoothed the background data. Sorry, I've actually rephrased it, that they smoothed the superconducting signal after taking this difference. Then, of course, you would have a smoother curve. So if that's true, then it's sort of hard to understand why you have anything like this that's so spiky. That remained strange. So we weren't really sure what was going on there. Then, so that's actually what we concluded here. So this jump at 171 is really very hard to understand. If there would have been any smoothing to take away the noise level that you see here to arrive at this, that would certainly also smooth this feature, and that doesn't seem to have happened. So we didn't understand. The other thing is that if you now take these 160 gigapascal data, this is on a range from -20 to 0. If you expand that range, then of course you have to display this part and that part separately if you both want to show it. So that's what we did. We separated it in 2 panels, expand the range. So this is now a range of 1.5 instead of 20 as it was before. And now you see on this expanded range something really amazing. There are smooth curves over here separated by jumps in there also. So that cannot be the case after you did smoothing of the final result. That would certainly take away these steps, and it didn't. The other thing is that you can actually take this graph. You could imagine that you can just shift it up a little bit, and then it continues over there. And the same as this one, you could shift it up, and then you have a continuous curve from there to there, and so on and so forth. So we went through that exercise, and what it gave is that this curve here, those two curves, are the sum of two components, the smooth component and a series of steps. That's shown over here. This is the smooth component, the two panels, and that is the series of steps. Now, the smooth component, we did more analysis on. That for that, you have to go to these papers, International Journal of Modern Physics, and you will find that this is a 15-node cubic spline with natural boundary conditions. The fact that it's cubic means that if you take the fourth derivative of this curve, you get 0. We'll come back to that later on. This one is different. It's steps, right? This is steps, and actually the step part contains the superconducting transition also. So this describes the superconducting signal really, and this is something else of which we don't know what it is, and we have never been able to figure out what it is, frankly. So this is a much smaller scale. This is a range of about 1 over here. This is a range of about, well, the whole range goes from -23 to +2, so it's 25 all in all. So these are very different ranges. So this is a relatively small signal. This is a much bigger signal. We don't know what they are. Another way of analyzing the data is to go back to this curve and take the first discrete derivative from it. So you just take the difference of neighboring points in this curve. And it's densely plotted, so difficult to recognize the points. But if you just take the difference of neighboring points and you divide it by this quantized value, which was 0.1655 nanovolt, then you get multiples of 1. That's these blue lines over here. You see that partly already doing that makes that certain points fall on those blue lines, and others are still superimposed as something curvy. That curvy stuff over here, that is just coming from the cubic spline. So if you take it one step farther down, then you're getting closer to those blue curves. And certainly if you take the fourth derivative of it, the discrete derivative, then there's no contribution in here anymore of the cubic spline, because the fourth derivative of a cubic spline is 0, except where you go from one segment to the other, you get some noise, but otherwise it's 0. And so this fourth derivative that we have down there, that is the most interesting say part, the most interesting function if you want to analyze later on what quantized components could be present, for example, also in the measured voltage, and that's what we'll use it for. So that brings me to the second piece of diagnosis, and that's that of the raw data. So I take here the case of the 138 gigapascal. Now I also show the background curve obtained by taking the difference of measured voltage minus superconducting signal. This it looks quite smooth, but if you enlarge it, there's actually noise on that. It's also true here, but not in the superconducting signal. There's no noise over here. That's again just the sum of a quantized component and a smooth component. So if we now take this first discrete derivative that I already spoke about, then because this wiggle over here, the step, you get a wiggle, two peaks over here in the measured voltage. The background data is just, you start to see the noise a little bit better now. And in the superconducting signal, you may think this is noise. Actually, there's no noise in here. It all has to do with the steps and the smooth function. So we take that further down to the fourth discrete derivative. And again, this background is just noise, more noise. And the raw susceptibility data also looks pretty noisy actually, but not the superconducting signal. There you see very nice horizontal stripes, and so those actually have to do with the fact again that this is apparently by and large the sum of a quantized component and this some kind of a spline function, which has no, which is just 0 if you take the fourth derivative of it. And so all that remains is the quantized part of it. You see it very clearly along the vertical scale. So what we did then is to go to calculate correlation functions. And the purpose of that will soon become clear, but essentially we just want to figure out if there's any signature of this here also in the measured voltage. That was the main purpose, and actually got one surprise there. So what are correlation functions? Well, you take this function delta n of chi alpha. Let's say you take the first derivative of that, is shown over here. And for the autocorrelation, you multiply it with itself, but shift it by j. And for the rest, you take the sort of scalar product of those series of numbers. And so if j equals 0, then there's complete overlap. You have only positive definite contributions, being delta chi alpha square, summed up. So that adds up to 1 after normalization. And then if you move away, you make j bigger and bigger, and you start to go down. At some point, you lose the correlation. So the width of this has mostly to do with the presence of this step over here. If you go to the background, if there were completely uncorrelated noise in it, between no correlation between neighboring points, then you still expect to find 1 over here, but then you immediately drop down to 0, which is something noisy. So the width over here has to do with the fact that apparently in this background data there has been some smoothing. And then for the measured voltage, since it is more or less dominated by the signal over here, it looks very much like the superconducting signal. If you now take the fourth derivative, then these features here become less important. It's still visible in the first, already in the second derivative, you hardly see these features anymore, and the first derivative is just gone. And so all you have there are series of steps. And so if you take the autocorrelation of superconducting signal with itself, then it's really you're looking for overlap of this step pattern with itself. And that works wonderfully if j equals 0, of course. You have only positive definite squares in this expression. You move away from it, and very quickly, after a few wiggles, having to do with this fact that it is a forced derivative, you get into the noise, completely as you would expect. For the background, it looks pretty much the same, and also for the measured voltage. So these autocorrelations are fine. You now go to the cross correlations, and here we'll skip this part and go right away to the fourth derivative. You see that there is no correlation between the background signal and the superconducting signal. It's just noise only. There is a positive burst between measured and background over here. So there is some correlation over here between these things, and this is the correlation of the noise present in the background curve. And then there's a very clear correlation again that looks very much like these graphs, these two, of the measured voltage and the superconducting signal. And that is really the correlation between those steps being present in the superconducting signal also being present in the measured voltage, which is surprising. Yeah. Okay, so why is that surprising? Well, to illustrate that, I'll go one step further here and first show you a simulation of what we would expect. So this is a simulation. These are fake data that I faked myself, and I made something that looked a bit like the kind of data we are talking about. So I made an independent background curve having its independent noise from a measured curve which has a superconducting step and then different noise from this one. And I took the difference from those two to get this superconducting signal. So since these are independent data sets, this correlation function that I spoke about before is just random noise. They are uncorrelated. Right? On the other hand, since the superconducting signal is the difference between those two, it inherits, so to speak, DNA from the mother and from the father. And so you will find that there's a finite correlation here, as you see in this graph, and there's a finite correlation here with the opposite sign because of this being the difference. It's MT minus BT. That's why this is negative over here. So it's clearly correlated, and that's very nice. So this is what you expect to find. If you go to the data that were published, it's not what you find. So this is now the case of 160 gigapascal, but it's the same for all 6 pressures really. There is between the father and the mother is now a correlation, as you see. Measured voltage and background are correlated. There's no correlation between father and daughter. There's no central burst over here. None. And there's a correlation between daughter and mother. So the family relation we have here is indicated. It's completely different. So it is the DNA of those two that got combined to create this very peculiar kind of family relation. That is actually an indication that instead of the superconducting signal being obtained by these two independent measurements and taking the difference, this tells you that those two are independent data sets and that the measured voltage was calculated by adding to the published data an independent background data set. Okay, that brings me to the summary. So the susceptibility data that were published in this Nature paper are essentially noise-free, and they have a sawtooth profile. Then the method by which the susceptibility data were corrected for a background signal is not correctly described in this paper. It's not true that they measured a susceptibility at a different pressure and subtracted those two from each other. 1.5 years later, two of the authors provided a different description that I'm not going to repeat. You just can look it up. And it is a very strange story. They actually give there's 3 different versions of it now. It's not sufficiently documented, and certainly that story involving what they call a user-defined background does not explain those pathological features of the right? Then there's a third very strange point. The protocol that has been used to generate raw data was not by measuring the voltage actually. So they are not raw data. What they actually did is, and they did it for all reported pressures, they took the published superconducting signal that had no noise. They took a featureless curve, which has noise, and added those two, and that is what was then presented as raw data. I have no knowledge about when these steps have been done in the history of this story, whether it was before Nature was published or after, but this is what actually has happened. That has a number of consequences, of course, and I like to talk about it because that's really the theme of this workshop. Physics is about phenomena that can be reproduced under identical conditions. That is our business. To make that possible, it is of crucial importance that scientific publications provide an accurate description of the methods of the data acquisition and of the analysis, and also of the data themselves. I also really think, by the way, that at the moment already of submitting a paper, authors should make available to the referees and the editor the data that they are, at least the data that are shown in the publication itself, because those are nicely and well documented. And also at the moment of publication, those data should be available. Now, the incomplete and contradictory information provided in Nature and then those 2 later archive papers about data analysis, that really inhibits the reproduction and verification by other researchers of the claimed room temperature superconductivity in this compound. This Nature paper has been retracted, by the way, but a proper explanation of all this stuff has never been given, and that's a very, very unfortunate situation, which is extremely damaging to the field of physics, and in particular to the field of superconductivity and high pressure research. Thank you for your attention. That was all.